In example 2, we're going to work on finding a solution to this differential equation analytically. To do that, we're going to go through three different steps, A, B, and C. In A, it says, what is the general solution to dy dx is equal to x? How do you know? The general solution to a differential equation is an equation that has a derivative of, in this case, x. In other words, we want to find the antiderivative of x to find the solution to this differential equation. If we find the antiderivative, we've got x squared over 2 plus some value c, some constant. We're using our power rule in reverse here, so our differential equation is just x, or x to the first. We would add 1 to the exponent and then divide by the new exponent. Part B, it says, explain why dy is equal to x dx, or why that's equivalent to dy dx is equal to x. So let's take a look at this equation, and what we're going to do here is we're actually going to multiply each side by dx. So I'll try to do that over here by multiplying the right by dx and the left by dx. Notice how the dx's will cancel, leaving us with dy is equal to x dx. And that's why they're equivalent. That's just multiplying the equation on the left by the same thing as we multiply on the right. We're allowed to multiply by that differential dx. We now want to figure out what the integral is of each side. So notice how if I multiply by dx on each side, and this is called separating your variables, in other words, getting y or something in terms of y on the left side only, and something in terms of x on the right side only. I know there's the d in there, but that differential is in terms of y on the left and x on the right. And what we're going to do here is we're actually going to take the integral of each side. I'm also going to add something in here. You could add a y to the 0 power if that helps you find the antiderivative. Y to the 0 is just 1, and 1 times dy is dy. And now what we're going to do is we're going to actually try to integrate each side. So we have to do the same thing to each side of the equal sign. We'll integrate y to the 0 dy and x dx. I'll show that to you over here. So if we integrate y to the 0, we have to add 1 to the exponent and divide by the new exponent. So that's just actually y. When we integrate dy, we just get y. On the right-hand side, we've got the integral of x dx. So we're going to find the antiderivative here, and that's the same thing we did in step A. So that was x squared over 2 and then plus c. Now, you might be wondering, why did we not use the plus c for the left-hand side? So to help you with that, let me go ahead and show you. And we'll do this in a different color. And we'll actually finish this one off and write x squared over 2 plus c here. That's going to be what we're going to want to write here for this one. That's the integral of dy on the left and the integral of x dx on the right. And once again, you're probably going to wonder, like, well, why aren't you adding the c in there? So if we did add a c in here, some constant, I'm going to say that's some constant sub 1. Sub 1 just means our first constant. And that's going to actually be different than the constant over here on the right, which would be c sub 2. If we subtract c sub 1 from each side, we're going to have y is equal to x squared over 2. And then c sub 2, or some constant, minus another constant is yet a different constant. So that would be c sub 3. Well, we don't need the c sub 3 if we just have one constant in the equation. We just usually write that down as c. So I guess you could say that those c's are there, but every time we're going to be able to subtract the c on the left or add, depending on what it is. And then we will wind up with just another constant on the right-hand side. So for these types of problems, you just want to work with one c on the right-hand side.